Hello, good morning, everybody. My name is Gwendalina, I'm from Vinova, and I'm presenting today a paper that we jointly did with the Intel Edge Computing team, and it's about how the structure of the video format can impact the efficiency of visual AI analysis. What is the motivation? Where it's been discussed also in other, in other speeches this morning, but there is substantially a mismatch between how video is consumed by the humans and how video instead needs to be analyzed by machines. In fact, human consumption tends to focus more on perceptual fidelity, and typically requires decoding the video at full resolution. As we've seen with Danny's presentation, you need to decode the 8K image before being able to do anything. While instead machine vision requires different things, because very often you need to maybe have a look at the video at a lower resolution to understand what's going on for detection, but then for feature extraction, low resolution is not enough because you're missing details, and not all the frames are equal because there are certain frames which include interesting information and some others don't. And the challenge is that if you are applying visual AI on traditional codecs, you need to decode the full frame, and we call it the full resolution tax because, of course, it costs a lot of pre-processing that sometimes cause the accelerator that then run the model to be underutilized. As an example, the workflow that we tested in Edge AI visual analysis started from an Ultra HD bit stream, which then needed to be decoded at full resolution and then downscaled to feed an AI model. In the case of the model that we tested, it was using a 448 by 255, which means that the model was actually working on 1.4% of the total pixels compared to the original, and over 98% of the remaining pixels were basically wasted. So how are we addressing this problem? And it's a very complementary way compared to some of the solutions that are being discussed this morning. We're looking at how a natively compute-aware data structure can actually be a complementary way to make the visual AI systems more efficient. And in particular, we tested two standards, two international standards. One is MPEG-5 LCEVC. In this case, we applied a base layer decoding first to do the detection, and then the LCVC enhancement layer can be used selectively to pull the necessary details, but only if it's needed. There's a second approach, which is MHV'26, which instead is a more flexible option, is fully hierarchical, and it's intra-frame, and it includes several layers of details that can be selectively accessed. And not only that, but it also allows to fetch specific resolution, specific color planes, and even specific regions within each of the levels of quality. To give you a practical example, using one of the videos that we use for our experiments, this is an Ultra HD surveillance video. Ultra HD compresses 0.6 bits per pixel, pretty good quality for either machine and also human perception. However, most of the information that you can see in this image are actually not very relevant for the machines. So what happens if we navigate the VC6 hierarchy and we select two levels of quality below what we call the LOQ0? In this case, we're looking at the 540p video, which means that it's 64% smaller in terms of size compared to the original picture, and is 1/16 of the pixel. So in terms of decoding speed, of course, is way faster. And with VC6, you can pool the data. So not only you decode at the low resolution, but you can actually fetch and pool exclusively the data corresponding to that level of quality. So in terms of data transfer and I/O, it's actually quite relevant. But you can go further down. I mean, in this case, it's a 270p video, which of course you would never use it for a human perception, but in order to detect the vehicle, it can be relevant, or to detect a broader region of interest to analyze further. And in this case, we're talking about an order of magnitude less data and 1/64th of the pixels. But then what happens if you want to do feature extraction? Because models are not very effective if they need to recognize the vehicle or even read the plate number. At that point, you can pool exclusively the pixels related to the vehicle. And we're talking about maybe 1% of the total pixels. So you can exclusively pool the data related to what you care about and feed the model exclusively with that, which means decoding very few pixels and transferring a very small amount of data compared to feeding the full 4K frame. So what did we do? We applied these formats, VC6 and LCVC, and compared against traditional video codecs like AVC and BVC. We use Intel's DL Streamer framework for video analytics, and we also importantly use the latest Intel Core Ultra 7, the so-called Lunar Lake processor, which also includes the GPU with the hardened AVC decoder support in order to test also high throughput applications. VSDROM dataset, a lot of Ultra HD traffic sequences, and the model was the SSD MobileNet for object detection, which was requiring a 448 by 256 input. And the evaluation focused on measuring the end-to-end system latency and throughput in the different scenarios, with the goal of course, maintaining the overall object detection through accuracy. So initial results, let's start with the first use case, which was LCVC on CPU. Decoding base only allowed to save 33% compared to native AVC decoded at full resolution, and 52% compared to VVC. This is, of course, because you are decoding a quarter of the pixels, which helps particularly with VVC software decoding, and also the detection component, the one in orange, is smaller because that includes the scaling, and actually scaling, starting from a low resolution, is a smaller operation. What happens then in GPU? Apologies for the graph, is a little PowerPoint formatting issue, but GPU is the same thing. We measure the throughput in this case, and once again, as opposed to AVC with the hardware decoder on the GPU, LCVC-based decoding allows to triple the throughput compared to native AVC and reducing by 66% the overall timing. In terms of the detector output, we measured the precision and the number of object detected, and this was enough to be able to say that, broadly speaking, the accuracy was more or less the same. But I mean, even eyeballing the clips, it was quite easy to see that actually was not making a big difference, because in any case, you have to downscale to a smaller resolution, so it was not making basically any difference. Moving to VC6, things are getting very interesting, and the outcomes are confirmed and possibly even enhanced. So in the case of VC6, we use a sparse inference scenario. So we did not analyze all the frames, but we sampled 1 every 10 frames. And so we compared VC6 against 2 AVC flavors, traditional AVC inter, but also AVC intra, to basically have an apple-with-apple comparison against 2 intra codecs. The interesting thing of VS6 is that there are two levels for improvement. One is that, of course, being an intra-frame, you can decode only the frames, the colon fetch only the frames that you want to analyze. And the second thing is that in order to feed the model, we could afford to use LOQ3, which was 8.6% of the total data. So basically, we only have to transfer a very tiny amount of data at very low resolution. And the result of this is that compared to AVC inter, which is a smaller file, so we normalized for quality, so AVC inter was a smaller file, but you had to decode the whole thing, while instead with VS6, you could decode exclusively what you wanted to analyze. So 96% reduction in the total time compared to AVC, and a 72% reduction compared to AVC intra, because we could decode a much smaller rendition. And this was in terms of timing, and this is instead the impact in terms of data transfer and I/O. As I mentioned, LOQ3, which was just enough to feed the model, was only 9% of the total. So the overall result is that in terms of I/O saving, we achieve a 30 times saving compared to AVC, and a 10x saving as opposed to AVC intra. So to conclude, what we want to bring to the attention is that the data format and the structure of your video is actually a complementary and important element that you should take into account when you are optimizing the efficiency of your visual AI models. We presented two different alternatives. LCVC is a retrofit path, and you can still achieve a pretty good savings in the order of 30 to 50% and 3x GPU throughput. And VS6, which is a full-fledged, fully hierarchical and queryable format, which can achieve order of magnitude savings compared to traditional codecs. There are a lot of next steps, so we're continuing the analysis, making it more sophisticated in measuring the accuracy in a more precise way. And more importantly, we're working with a lot of ecosystem partners in testing these video formats within state-of-the-art video analytics for applications, for inference, for training. And so we're very welcome to also collaborate with operators, with big video databases to see how the data format can complement their effort. Thank you very much.